We'll be taking thermodynamics 2 now, and we'll be looking at the Clapeyron and the Clausius-Clapeyron equations. Now, before we talk about everything we are doing here, these equations are used when we are looking for the enthalpy or a certain kind of enthalpy. So, in this case, enthalpy of vaporization. The enthalpy that is needed to change phase, right? So, from liquid to gas or gas to liquid, especially. Right. And remember we said that the change in enthalpy dH was equal to TdS minus V dP. Now we realize over here that we are looking at ds and dP, right? So we're looking at how entropy and pressure are going to change. So remember our Maxwell relations. We had a relation where we're considering how pressure was changing with respect to a term and how entropy was also changing with respect to a term. So this is the Maxwell equation we use in the derivations we are about to do. Now the other equations could be used, but you realize that for those other equations you end up having something like del T del P at constant S being equal to del V del S at constant P. You don't want a case where we are going to be keeping the entropy constant, right? So we want to avoid that. So this is um, the best relation to use for the proof we are about to do among the Maxwell relations. Okay. Now let's work with the Maxwell relations now and we'll come back to our change in enthalpy formula. So we are looking at del S del V at constant T, right? And now we want to do we want to consider a phase change. If we are considering the change in phase, right, it means that temperature and pressure are going to be kept constant. Okay, so because temperature and pressure are going to be kept constant, we'll be having a change in phase, and a change in phase means that we are moving from either liquid to gas or gas to liquid or anything like that. So our del S del V at constant T, we can approximate it in this form because, as we said, we're looking at a change in phase. So you're looking at the entropy when it's in the gas phase minus the entropy when it's in the liquid phase for the del S part because it's a change in phase. You're looking at the entropy when it is in one phase minus that when it's in the other phase, right? Over the specific volume when it's in the gas phase minus the specific volume when it's in the liquid phase. So the specific volume when it's in one phase minus that's when it transitions to the other phase. Okay. Now we said that dH was TdS plus VdP. Oh, so sorry, I said minus VdP earlier. So that was a mistake on my part. It's plus VdP, right? And now remember we said we are keeping temperature and pressure constant because we are dealing with a change in phase. So it means that there can't be a change in pressure. Pressure has to be constant. So the P would have to be 0. That means that this expression has to go to 0. That term has to go to 0. At the end of the day, we end up with dH being equal to TdS. Now this is the essence of the formula we're trying to derive over here for equation 1, right? We'll see the essence very soon. So let me point this out. We can simplify this. We know that SG minus SF, right? We can represent it with S of SFG, S subscript FG, right? And then VG minus VF, we can represent it with VFG, right? Okay. Now, if we take our dH being equal to TdS, you can integrate both sides. You can integrate dH. Once again, it's a phase change. So from the enthalpy, it may be the liquid phase, the enthalpy in the gas phase, being equal to T is a constant because once again, it's a phase change. So I can bring the T out. And then the S, so from the entropy in the liquid phase to entropy in the gas phase. So if I should do this, I'll end up getting Hg minus Hf being equal to T Sg minus Sf. And when I do that, I'm going to get here Hfg being equal to T SFG. That's what I have for equation 2, right? Now we can replace SFG in equation 2 with the SFG expression from equation 1. Or we can, yes, we can substitute this in equation 1. So if I make SFG the subject in equation 2, I'll have SFG to be equal to HFG over T. So I can put this in equation 1. Equation 1 was del P del T at constant V was equal to SFG over VFG. So I can replace this SFG now with what I have down here, so that this side becomes HFG over T times VFG. So that's what we have down here. So let's say this is equation 3, right? So we have del P del T at constant V to the HFG over T VFG. Okay, now we can take this even a bit further. So our focus is on HFG, so we can make HFG the subject to get the expression in this form. And then using the central difference approximation from the steam tables, we can write del P del T at constant V in this form, where we have P2 minus P1 over T2 minus T1. Or we could say that maybe P at T plus change in T minus um, P of T minus change in T. So I'm representing this with P2 and this with P1, right? All over our T2 minus T1. So yes, using the central difference approximation from the steam tables, we can write del P del T at constant V in this form. So that we can replace this here with that so that we get this expression, right? But remember, it's an approximation. The central difference method was an approximation. It gives us an approximate value. So it means that this expression at the left-hand side is going to be approximately equal to HFG, because del P del T at constant V is approximately equal to that value, right? Okay, the value can be very close, but then it's not going to be an exact value. Okay, so that's what we call the Clapeyron equation. Right, this equation right here is what we call the Clapeyron equation. Okay, now we have what we also call the Clausius-Clapeyron equation. And for this one, we are going to consider very low pressures, right, and very low temperatures. We can use this for points on the steam table that are very low. Now, our very low pressures, what we realize from the steam table is that Vg is going to be far greater than Vf. That's the specific volume of gas is going to be far greater than the specific volume of the liquid. So what can happen is that if I take Vg minus Vf, because Vg is far greater than Vf, the expression will be approximately equal to just Vg, right? If Vg is way larger, I think, let me pick values from the steam table. I think, okay, I didn't put the steam table in this one, but I can pick some values right now. So at a pressure of, let me use 1 kPa, that's a pressure of 1 kPa, right? The Vg we are getting is 129.2 meter cube per kilogram, and the Vf we are getting is 0.001, right? So it's actually safe to say that this is approximately equal to just 129.2, but the value is way larger than the value of Vg is way larger than the value of Vf, right? If we should actually compute this, we'll be getting 129.199, which is approximately equal to our 129.2. So what we are saying is that when the pressures are very low, right, we can express VFG to be approximately equal to just Vg, because the Vg value is far greater than the Vf, right? So we can just express it as Vg, or we can assume that since Vg is dominant, it will be equal to VFG. Okay, so that's what we are going to be using. Now, once again, when we have very low pressures, we can assume that our gas is ideal gas, right? So we can assume we're working with an ideal gas, and for the ideal gas equation, considering 1 mole of a gas, PV is equal to RT. So we can express our V as RT over P, right? But realize that we are dealing with a specific volume now. That's our Vg, right? And we want Vg to be in meter cube per kilogram, because that's what we read from the steam table, right? So it means that the R we have to use has to be in kilojoule per kilogram Kelvin, right? And that means that it has to be the specific gas constant. So it will be R over the molar mass. That's going to be 8.314 over the molar mass of the gas you are working with, right? So we can actually understand it from this point. We can say that PV is equal to nRT, right? So PV is equal to M over mRT, right? Now, if we want the specific volume, we can make V over small m the subject. If I do that, I'll end up with R over M T over P. The R over M here can become my specific um, gas constant, right? So I can represent this with I don't remember if it was a heart symbol that they used, but you understand what I'm trying to say, right? So that we can have V to be equal to RT over P. So the R here is specific. It's not 8.314, it's 8.314 divided by the molar mass of what we are working with. So we can get a specific volume in meter cube per kilogram, right? Okay. So yes, we spoke about this. We said that VFG is approximately equal to VG, and that's essentially considering an ideal gas because we're dealing with very low pressures. We can say that V is equal to RT over P, right? So I realize that we are dealing with the gas, so the V here is going to be the specific volume of the gas. So we can just say that VG is going to be equal to RT over P, right? Now remember we also said that VG was also going to be equal to VFG. So from the equation we had earlier, this equation down here, we can replace VFG with RT over P, right? So if we do that, we're going to have a HFG over T times RT over P. And if the P is divided, it means we can bring it up here. So that's what we've done over here, right? And we can simplify it to get a PHFG over the T can multiply the other T to give us T squared, and then we have our R. So now we have what we call the Clausius-Clapeyron equation, right? And for this equation, we are saying that this is all equal to del P del T are constant V. So for this equation, we can actually find a relation for del P del T are constant V, right? Okay. So we'll see examples very, very soon. So the Clausius-Clapeyron equation, we can use it for phase change from solid to gas as well. Right, so that's one thing about this equation. We can use it for enthalpy of sublimation. When we are considering the change in phase, we are saying that pressure varies only with temperature. So there's no need for us to deal with the partial derivatives. Right, and now we're seeing what I mean by that. So remember this expression over here at the left hand side, del P del T are constant V. That's what we are coming to talk about. Right? But I realize we are dealing with a phase change. So it means the pressure is going to vary with respect to um, only temperature when we are working with change in phase, right? Okay. Um, yes, so with change in phase, I think the pressure is going to change um, if temperature should change. But with phase change, pressure and temperature are actually constant, so they are dependent on each other, right? What we are trying to say is that because pressure and temperature would be dependent on just each other, they are not going to depend on any other term, right? Then we can, instead of working with the partial derivatives, we can work with total derivatives now. But the partial derivatives imply that pressure is changing. For this one, it means pressure is changing with respect to temperature, right? But in another case, pressure was also changing with respect to another variable. That's why we are working with the partial derivative. So this is how pressure is changing partially with temperature. But now we are seeing here that when we are dealing with a phase change, it's just going to vary with temperature. So if I should change the temperature of the system, right, I will change the pressure of the system. And it wouldn't depend on anything else. So because it's not going to depend on anything else for a phase change, I can just use the PDT. And this time it is at saturated conditions, right? But when actually doing a phase change, um, yeah, I mean that's what we are going to end up getting. So if I should um change the temperature of the system, then I'll be changing the pressure of the system. Or if I should change the pressure of the system, then I'll be changing the temperature of the system. Okay, so let's continue from there. So we can see that del P del T are constant V is equal to our HFG times P over RT squared. But we are saying that del P del T are constant V is the PDT saturated. So we can end up with this equation. Now we have a separable differential equation, right? So we can take the P over P. All of this is at saturated conditions now, right? So I can send the P over, so I have the P over P at saturated conditions, and I can send the dt here to this side as well. But I have my HFG over RT squared, squared over RT squared dt also at saturated conditions. So that's what we have over here. Now, if I do the integration, I'll get the last equation we have at the bottom of this page. So if I integrate 1 over P dP, right, from P1 to P2, I'll get ln P2 over P1. So that's what we have over here. And if I integrate HFG over R, I'm taking them to be constant, right? Yes, HFG over R are taken to be constant for this equation here. So I'm going to integrate my 1 over T squared dt from T1 to T2. I can write this as T to the power minus 2, right? So if I integrate, I have T to the power minus 1 over minus 1. Right? So that's minus 1 out. 1 over T2 minus 1 over T1. And that will be 1 over T1 minus 1 over T2. So that's what I have down here. So you can actually take your time and work it out as well. I'm sure the integrations should be easy because by now you would have done differential equations. So separable differential equations wouldn't be a problem. Okay, so we can take it from this point now. So this is going to be the final form of our equation, right? Now realize that we have two temperature points, and between two temperature points, HFG is not um, going to be constant. But when we are dealing with very, very low temperatures, the HFG values can be very, very close to each other, right? So we can assume a constant term for them, or we can guess or approximate what the term should be, right? So the Clausius-Clapeyron equation is going to be more accurate when we are dealing with conditions of very, very low temperatures. And one advantage of this is that it can help us approximate values below the values of our given steam table. So the steam table in Shums, for example, ends at it or begins at a temperature of 0.01 degrees Celsius. What we are saying is that we can do our approximations for conditions below this value, even though it's not on the steam table. And what we'll get to be very accurate because he said at very, very low temperatures, the Clausius-Clapeyron equation will be accurate, right? So, one thing we said HFG is not constant, so we can take an example from the steam table in Shums. If we look at a temperature of 0.01 degrees Celsius, our HFG is 2501.3 kilojoules per kilogram, right? If you look at the temperature of the next temperature they have here is now 3.8, so the value is 2492.5 kilojoules per kilogram. So realize that it's not so much of a difference considering the change. I mean, from 0.01 to 3, you're getting a difference of about 8.8, right? So you realize that it's not going to be so. That's from 0.01 all the way to 3.8. Let me pick values that are a bit closer to each other to make this easier for us to relate to. Um, yes, let me use 12 and 14. So at 12 degrees Celsius, right? When we have 12 degrees Celsius from the steam table, all we'll have is 2473.1 kilojoules per kilogram. So you can get your steam table and verify this with me. Then at 14 degrees Celsius, what we are getting for HFG is 2468.2. So if we look for the difference between them, we are getting a value of about 4.9, right? That's not so large for a temperature change of 2, right? A change in HFG of about 5 is not so large. So with these kind of things, we can approximate or guess what our HFG value should be when we are not given a particular temperature and pressure. So we'll take an example so that we see what we are talking about very soon. But basically, what we are saying is that the Clapeyron equation, we can use it for two phases in equilibrium. The Clausius-Clapeyron equation will do the same thing, but then we are dealing with the assumption that the gas is ideal. Right. The only time we consider ideal gas for the Clapeyron equation is if in the question it states that we should consider an ideal gas, so that our equation of state becomes the PV is equal to RT. Right. Okay. So just keep that in mind. Now, aside this, the Clausius equation will look at equilibrium between solid. That's the Clausius-Clapeyron equation, right? We look at can also consider equilibrium between solid, liquid, and the gas phase, right? So, like we're looking at maybe the transition from um maybe solid to liquid, or the transition from from solid to gas, or the transition from liquid to gas. That will be for the Clausius-Clapeyron, right? But then the um, Clapeyron equation can consider solid and liquid, solid and gas, liquid and gas. So we can do solid to liquid, solid to gas, liquid to gas, right? Okay. So that's just one thing to keep in mind. For Clausius-Clapeyron, we just want to look at how solid and liquid will end up getting us to the gas form. Okay, so we'll take some examples. So this from Sean's. We want to predict the value of the enthalpy of vaporization for water at 200 degrees Celsius, assuming steam to be an ideal gas. So you're looking at the change from water to gas, right? So we can use our Clapeyron equation. Realize that we have a very high temperature, so Clausius-Clapeyron is not going to be so convenient in this case. But we've been told to assume we are working with an ideal gas. Okay, now the Clapeyron equation, we derived it to be this, right? And we need to work with absolute temperature. So T is going to be 473.15 Kelvin. Now VFG is going to be VG minus VF. Okay. Yes. And the question told us to assume we are working with an ideal gas, right? So we can use this to approximate the specific volume of the gas, right? We are not going to assume that now VFG is going to be equal to VG, or approximately equal to VG, because you realize that we have I'm coming, yes, realize that we have very high temperatures. So at that point we will not be dealing with that assumption, right? Because when the temperatures are very, very high, that assumption doesn't really hold. A second. Yeah, when the temperatures are very, very high, that assumption doesn't really hold well, right? So you can verify from the steam table, you can check very high temperatures, realize that Vg is not far, far greater than Vf. So we can't say that Vfg, which is Vg minus Vf, is approximately equal to just Vg. So we need to find both Vg and Vf. So the ideal gas equation assumption we are using is going to help us find just the specific volume for the gas, just Vg, right? Now, we know that Vg is going to be equal to RT over P from the ideal gas equation. And our R, as we said, is the specific gas constant. So we are dealing with steam, which is water. So the molar mass is going to be 18. So we divide the R by that to get 0.462 kilojoules per kilogram, right? We know our T, which we said was 473.15 Kelvin. And then we know our pressure. So we can check the pressure from the steam table at um, T being equal to 200 degrees Celsius. Realize that the saturation pressure there is going to be 1554 kPa, or if it's in megapascal, you see 1.554. So we can check the steam table at 200 degrees Celsius to verify that, and realize that that's going to be the value 1.554 megapascal, right? The reason why you're picking the saturation pressure is because you're dealing with a phase change. And our phase change, we know that our system is going to be saturated. So we pick the saturation pressure for that calculation. So that's what we have here. So our VG is going to be 0.14062 meter cube per kilogram, right? So as I said, P was read as the saturation pressure of steam at 200 degrees Celsius, and I change the value to kPa. I want to find the volume of the liquid, right, in the liquid phase. So for VF, we can use the density of water to do this, right? Because you know that V is equal to 1 over rho, or the specific volume is equal to 1 over density, right? And for water, we are going to assume that the density is going to be fairly constant. The density wouldn't change by much, right? So it means that the VF, I can represent it with 1 over the density of water. The density of water is 1000 kilogram per meter cube. So that my VF becomes, I think, 0.001, yeah, meter cube per kilogram, if I'm not mistaken. Okay, did I speak about that? So it will be 1 over 1000 basically, right? It will be just 1 over 1000. So it will be 0.001 meter cube per kilogram. Or you could actually go to 200 degrees Celsius and read the VF from the steam table. That's also fine. And I personally would prefer reading it from the steam table because I feel like even though there's not going to be so much of a difference, it would give me a more accurate answer, right? So we can actually compare. When we read VF from the steam table, we are getting 0.001156. If we had done 1 over density, we would have been using an approximation of 0.001, right? So we see that the difference between the two is just going to be the extra terms here, right? So that would be about 0.00015. So that's the difference between the two, right? So yes, I would have preferred reading from the steam table. So reading VF from the steam table, I'm going to get this value, right? But the question said we should assume an ideal gas. So um, I would rather use that formula to get VG instead of picking the VG from the steam table, because from the steam table, if you had read VG, you would have been getting 0.1274, right? But when we use the ideal gas approximation, we had VG to be 0.14062. So we use what's in the question because we are assuming it's an ideal gas, right? Okay, sure. So we can put all the terms in our equation. So our equation was this. Yes, this was our equation, right? So we have our T, we have our VFG now, which is VG minus VF. So we found VG, we found VF. Now we use the central difference approximation to find um, P2 minus 1 over T2 minus T1. And I intentionally used the value at 200 degrees Celsius when I was talking about finite differences, the video on finite differences, so that we would see that we'll end up with the same expression. So we are looking at the change in pressure with respect to the change in temperature, right? At T being equal to 200 degrees Celsius. So we use the central difference approximation, right, to get our P2 minus P1 over T2 minus T1, and we ended up with this. So if you've not checked out that video, I would advise that you actually go to that so that you understand what we mean by the central difference approximation and realize how we found this expression. I actually solved this particular expression in that video so that we can relate it to this um, discussion, right? So when we put all these terms in here, we'll end up with this value for HFG. Okay. So another example we have here, we are supposing that the steam table started at saturation pressure of 2 kilopascal, right? That's with a saturation temperature of 17.5 degrees Celsius. And now we want to find the saturation temperature when a saturation pressure is rather 1 kilopascal. So we are trying to predict the saturation temperature. Right, so we assume that our steam table started from 2 kilopascal, but I want to find the saturation pressure at 1 kilopascal. So now because we are working with values below our steam table, we can use the Clausius-Clapeyron equation. All right. Okay. And once again, we are dealing with very low pressure, so we can assume an ideal gas. And we can also work with the assumption that V is far, far greater than VF because it's very low pressures. So our VFG will be approximately equal to our VG, and we can use the Clausius-Clapeyron equation because we are dealing with an ideal gas, right? And we are working with very low pressure. So we can model this with the Clausius-Clapeyron equation. Very low pressure is giving us this. So we can model this with the Clausius-Clapeyron equation. So this is our Clausius-Clapeyron equation. Oh yes, I actually included the steam table at the that aside. I think I should have brought this earlier in the video, but it's fine. So we can see some of the things I spoke about earlier are very low temperatures, right? Very, very low temperatures. VG is far, far greater than VF, right? And then we can also see that for HFG, right? When we are at very low temperatures and pressures, they are not so far off from each other compared to when we have very, very high temperatures and pressures. So if we consider a case like, it's not on the slide here, but if we check the steam table from Shams at 370 degrees Celsius, that's a very high temperature, right? The pressure was also 21.03. The HFG was 442.2. But then at 360, that's just a difference of 10, right? The HFG was 720.7. So these are high temperatures and pressures. You see that just with a difference of 10 degrees Celsius, we are getting such a large change. We are getting, we are moving from 442 to 720. But with what we are even doing here, I can move from 7 to about 17, right? That's also a difference of about 10 in terms of temperature. But my HFG is moving from 2484 to 2460. It's not so large compared to when we have very high temperatures and pressures. All that we are trying to say is that when we are dealing with low temperatures and pressures, our HFG values are not remarkably large, right? Okay. Now we want to find Tsat at Psat being equal to 1 kPa. So I can make P2 the 2 kPa, right? Which means that T2 is going to be the saturation temperature at the 2 kPa, which was given to us in the question as 17.5 degrees Celsius, right? And then I can make my P1 the 1 kPa, which means that T1 is the unknown I'm looking for. So that's what we are going to do. So we'll put in the expressions for the values for P2 and P1, and then for the corresponding T's, right? So it means that we also need to find a value for HFG and for R. For our R, we already know our R is going to be the 8.314 over 18, right? That's going to be the specific R. And now we need to get an approximation for HFG. So now let's go back to the steam tables. At 2 kilopascal, the HFG is 2460. This is in megapascal. So multiply everything by 10 to the power 2 to get it in kPa. So at 2 kilopascal, the HFG value was 2460, right? At 3 kilopascal, it was 2444.5. And then at 4 kilopascal, it was 2433.0. Now, if we want to find the value at 1 kilopascal, we have the value here on the steam table, right? But we are assuming that the steam table doesn't get here. So we want to find the values here, right? So it means we don't have any of this data. Now, if we want to find if you want to assume a value for 1 kilopascal, right, we can just look at the trend. So from 4 kilopascal to 3 kilopascal, we have a difference of about 10.5. From 3 kilopascal to 2 kilopascal, we have a difference of about 15.5, right? So we see that the increase is about 5, right? So I can safely assume that from 2 kilopascal to 1 kilopascal, my difference could be about maybe 20.5, right? So if I add 20.5 to 2460, I'll have 2480.5. So I can work with 2480.5. I can assume 2480.5, right? I actually assume 2478 for this particular question just to show that even if the values differ slightly, so maybe it was 10.5, 15.5, and then I rather added, instead of me adding maybe 20.5, I rather added maybe about 18 instead, right? You can do something like that because 18 is not too far from 20.5. So you can add values very close. You can just assume it. And I'm saying this because maybe for how you would look at the trend, you see, if I realized that the difference in this was plus 5. So I decided to add maybe plus 5 to it, right? But then somebody might not really look at it from that perspective. Somebody might be like, oh, 10.5, 15.5. Maybe the next thing, or maybe from the trend you get, the next thing might not really follow through like that, right? Or you might have compared different values. Maybe you compared 2, 4, and 6 and looked at the trend there, right? So we can even try that out. So if we compare from 6 to 4, the difference is going to be about 33 minus 15 is about 18, right? So from 6 to 4, then we can look at maybe from 4 to 2. So the difference over there is going to be about yes, almost 16, right? So maybe from 2 to 1, I might be looking at something around these values as well. So it just depends on the trend. You just look at the values you have for at least 3 values, right? Look at the trend and see an approximation you can get. Okay. So I assumed 2478 for this question, right? But you could have assumed the 2480.5 as well, and to be fine. I assume the value close to this value, right? You could have assumed 2408.5 to be fine. I think in Shums they actually assumed 2480. This is what they actually worked with. Yeah. So we can put that as a value for HFG, right? So let me just go over this part again. What I'm saying for the HFG is that We want to find an approximate value for HFG at the temperature, at the pressure we are looking for. But we assume that our steam table ends at 2 kilopascal. So we can't work with any of the values below it. So for 2, 3, and 4 kilopascal, I can look at their HFG values, see the trend. Okay, how much does it increase by or decrease by when I move from one value to the other and from one value to the other? Okay, so if I look at that trend, how much increase can I assume it would have up to the point of interest I'm looking at, right? So just look at the differences between the two, and then assume something reasonable, and then you put it in as your HFG. Once the value is very, very close, you should be fine. Or once you follow the trend, you'll get a value that's very, very close, and you should be fine. So I assume 2478 kilojoule per kilogram at 1 kilopascal, right? Because I was using the change from, we assume the change from 2 to 1 should be about um 18 kilojoule per kilogram, right? Okay, yes, okay. So all we can do is that we can put all those parameters inside. So I know I took my P2 to be the 2 kilopascal. So it means that the T2 is its corresponding saturation pressure. That was the 17.5 degrees Celsius. And my P1 is the 1 kilopascal. So my T1 is the unknown, right? So I can put all these expressions in there now so that I have ln P2 over P1, which is going to give me ln 2 over 1 to be equal to my HFG, which is 2478 over my R, which should be the 8.314 over 18. That's, I think, 0.462 times my 1 over my T1, which is my unknown, minus my 1 over my T2, which is 17.5 degrees Celsius. But I'll have to express it as an absolute value for calculation purposes, right? So I can simplify this and make T1 the subject. When I do that, I'll end up getting I'll end up getting a value of 280.128 Kelvin for T1, right? Yes, it was supposed to be T1 over here because I made P1 the 1 kilopascal. So the unknown is supposed to be T1, right? Or I can find this as 6.978 degrees Celsius. And from the steam table, that the value was actually 7 degrees Celsius, which is quite close to our approximation. So at 1 kilopascal, the value was actually 7. Right? So our approximation gave us 6.978, which is also quite close, right? Now, I could have decided to make, instead of making P2 the 2 kilopascal and P1 1 kilopascal, I could have rather made P2 the 1 kilopascal and P1 rather the 2 kilopascal. All that it means is that my T1, right, is now going to be the saturation for the um 2 kilopascal, the saturation temperature for 2 kilopascal, and then my T2 is now going to be my unknown. So I could have, instead of making it ln 2 over 1, I could have made it ln 1 over 2 to be equal to 2478 over 0.462. Now I'll know T1, right? 1 over my T1 is going to be that for the 2 kilopascal. So that's the 290.65, then minus 1 over my unknown T2, right? I'll end up getting the same thing. It's the same kind of expression. So whatever you choose for P1, make sure that it corresponds with T1. Whatever you choose for P2, make sure it corresponds with T2, and you would be fine. Okay. So that'll be it for now. Thank you very much.